Well, actually, so let me start. What is the topic today? Yes, fluid flow. How fluid flows in porous media. And in general, remember your basics when you were in high school. When you want to know how things move, basically you go back to momentum and energy conservation. And remember, you could solve problems either by energy or by momentum conservation. Sum of forces equal mass times acceleration. That's momentum conservation. Or the sum of energies constant, total energy constant. So this is what we are going to deal with, how fluid moves. And in general, for porous media, one of the characteristics of porous media is that the size of through which water is flowing, or any fluid is flowing, is very small. So viscous forces are important, and therefore we are going to talk about very slow flow. Slower than laminar. So it's not just laminar flow. Slow laminar flow is usually, not always, but usually what we will have to deal with. And yeah, this is a concession. I knew that John was starting, so this is our business. And it is important to keep a balance. It's important to keep a balance. I'm going to talk about momentum conservation, and sometimes we get so carried along with momentum conservation that we forget that our business is dealing with water. And during this course, we might. The other risk is that we get so flowery about solving the problems of humankind and responding to the questions of God that we forget about the basics. So, look far, but keep the feet on earth. And I'd like to start with this, solving the problems of humankind, because Darcy contributed to increasing life expectancy for 20 years. And these are the expected life expectancy. Anyone listening to me, I like to use this transparency a lot. The increasing life expectancy in France, it is in France because Laplace was French. And Laplace, who founded the statistics, said, wow, this is very powerful. He had a dream. And he sort of started having the French government keep statistics of everything. So many years later, this British guy said, well, how does life expectancy, what controls life expectancy? And he found that treating wastewater and providing safe drinking water contributed to increasing life expectancy by some 22 years. Life expectancy has grown since then some 50 in developed countries. Of those 50 years life, which is a lot, 32 years at the mid-19th century, 150 years, almost 200 years later, we are at 80 plus. So 50 years increase in life expectancy, 22, 23, thanks to these guys, not just Darcy. And the point is that Darcy was not aware he was doing that. He just had a problem to solve. He had to supply water, and at that time they were starting to, basically in France and United Kingdom, Germany, say, shit, when we provide water, we are also providing pathogens. This is the times of Pasteur. They were finding these things. They say, well, perhaps we should filter it. So the question was, how do we filter water? You don't have to think that you are solving the problems of humankind, my friend John Selker. What you have to be is keep your feet on earth and say, I am solving this big problem, not a problem of humankind. It took another 50 years to realize that these guys were really solving the problems of humankind. You do your best, you enjoy it definitely. And Darcy, who was a civil engineer in trying this to solve this problem, said, well, how big should the filters be, whatever? So he had this very basic question, and all he did was say, well, I do experiments with a very simple column that I make water flow through, and what is it that controls how much water goes through? And, well, he did experiments with different column heights, with different cross sections, with different flow rates, with different grain sizes, well, just to see what it controls. And basically what he found was that Yeah, the flow rate is proportional to the cross-sectional area, is inversely proportional to the length of the filter, it is proportional to the difference in elevation of the water at the two ends, and that's basically the way he formulated it. Huh? The flow rate is proportional to these things, inversely proportional to the length, and that was it. Well, he was an engineer, he didn't care about anything else, and that's, I solved my problem, I know how to design filters. And then but still, it was a fancy experiment, it was a nice experiment, so he presented it in the Académie des Sciences, did I say it right? And there was this, another guy there, a polytechnicien, who hasn't made it to history, Dupuy. Dupuy, he was a polytechnician. Oh, but what you are doing is the same as, the experiments are the same as Fourier. Fourier was also a very interesting character. Eh? So this is exactly the same thing as Fourier. So everything that Fourier did applies here as well. And that's, so the first guy who wrote it the way we know it now was Dupuy, really, who was a polytechnicien, so he had this, you know, mathematical training and way of thinking, and he realized it was the same as Fourier experiments. But Dupuy was too humble, huh? So he didn't make it to history. Fick was even cheekier, because Fick didn't do anything. He looked at the experiments that a British guy had done, Graham, and looked at and read Fourier's book and said, "Oh, this is the same." Fick's law. So, anyhow, so this is Darcy's law.
He's got two laws.
Excuse me, two exactly. This even cheekier. So, yeah, this law, if you put here diffusion coefficient, here concentration, and here diffusive mass, this is called first law. Then the mass conservation is the second law, which is also a direct copy of Fourier's heat conservation. Eh? So anyway, so this is Darcy's law. Now the point is, here there are several things involved here. So we have this head. What is it? Is it a potential or is it not? What if we work with different fluids? What if we don't do it in a pipe? You know, what is the validity of this in general? And so the rest of the lecture will be, I hope, devoted to that. I would like to use the screen for a little while. So can I, but I wouldn't like to turn this off. So can I put lights on the screen? Let's try. No, this is not it. But that will be fine. So the first question is, what is its head? What drives water flow? And we can define it in different ways, the concept of head. So here I am going to discuss several things. The first one is head. And head, the concept of head is a much older concept. Now Darcy was mid-19th century. Actually, the concept of head is 18th century. And really what it is you have to imagine a flow tube, any kind of flow tube. This doesn't have to be a porous medium. Huh? Or it's valid for the atmosphere, it's valid for water in a lake, in a river, whatever. But we have a flow tube that water is, or I mean, any fluid is flowing through here, so I am already responding to some of these questions. And I say, well, let us assume it moves freely. There is no energy dissipation or whatever. So the energy of the water moving here should be the energy the same as the energy of the water moving over there, which means that, well, I have to compute the energy here, and the energy here would be, if I have, let's look at the volume of water or fluid moving over there. So the energy, we have, well, the kinetic energy. So I have the volume, capital V, times the density, times V squared divided by 2. Let me put the V like this, not to be confused. So this is 1/2 of mv squared that you all. So we would also have the potential energy. Remember mgh. So the potential energy, in this case, if I am working this volume, it would be V rho g h. Well, h, Z, some elevation. So I have some reference plane, and I put the elevation here, Z. Plus, I also have, if things are moving, this is pressing, so there is some work that is being applied, mechanical work, which would be what? Pressure times the cross-sectional area. So let me put here the cross-sectional area, which of course will evolve along the flow rate. So all these things change along the flow line. So that times the distance covered, which could be delta x, let me put here, or delta s. And I guess well, I guess this should work, huh? So this is the total energy, the energy, kinetic and potential energy, plus the work that I have to apply to move all those things, and that should be constant. That should be the work that the energy plus the work that is done at the end. And it's not very computed, so this is sort of energy. Energy, and I actually well, that's fine. This is not very convenient. Remember that, I mean, usually we work in energy per unit mass. So we can divide by mass, and the mass here would be the volume times density. And if I divide by the volume times density, and the volume here, by the way, is A delta S. So this is the volume of water. PV is the work that I apply. So if I divide by V rho, what I end up, energy per unit volume, per unit mass actually, per unit mass, which is typical potential. Potentials are typically energy per unit mass. So this cancel is V squared over 2 plus Gz plus P over rho. But this is too complex for engineers because this has weird units, joules per kilogram. Or if you, or it's also kind of an acceleration times distance. It's kind. I mean, think of these units: meters squared divided by second squared. It's too complex. So since it is too complex, we say no. This is not convenient. It is much better to do it per unit weight. So if I put energy per unit weight, then weight is acceleration of gravity times mass, so I divide all this by g, I end up with the famous v squared over 2g plus z plus p over rho g. And this is the head. This is what Bernoulli proposed as what should be conserved when a fluid is flowing. And the most amazing thing is that the concept of energy is also beginning of the 19th century. It was Laplace and especially Fourier, all these guys. How could Bernoulli in the 18th century do it? And so he didn't do it like this. He did it by conservation of momentum. And it can also be done, I prefer not to do it by conservation of momentum. So this is by energy conservation, because you have to use Euler's equation. The formal derivation is using Euler's equation that no one understands. I mean, we all know the formalism of how to derive them, but the implication, no one knows. So I feel uneasy, and I would not convey that to you, so I am not going to do it. However, there is this is the best way to derive the concept of head, using momentum conservation, the formal momentum conservation, which is not the one, this is not the one that Bernoulli used. But it is important because it is the only one that really tells me that yes, we have a potential for fluid flow. Even here I was very happily divided by rho g, as if rho was a constant. But then when you work with air, or even when you work with water, with big deep differences, the compressibility of the fluid is important. And all these concepts are good even if the fluid is compressible. The only thing is that, properly speaking, this term over here, if you want to take into account compressibility, you should use this definition. So it's the integral of P divided by rho, of dP divided by rho. So this term, if you want to formally take into account the fact that the fluid is compressible, is like this, between P ref and the actual P. So this is the piezometric term. Now, what if density also changes because of you have temperature changes? Temperature changes and then the fluid expands and then density changes. Or if you have changes in concentration. You have in some places you have a high concentration and other places a low concentration. So the density depends not only on the pressure but also on temperature or concentration. Head, energy per unit weight. Energy per unit weight, and it is, P over rho G. Sometimes we write gamma there, plus C plus V squared over 2G. Actually, this is too difficult for us. Groundwater is the field of geology. Are there many geologists here? Very few. I am very disappointed. Yes, because I'll make it clear later why it is so important to have geologists. But geologists hate mathematics. What is this? This TV show that the Big Bang Theory. You know, it's the physicists on the one hand, say, well, geology, they study stones. Who cares? So this is too complex. V squared there is killing for a geologist. But the good thing is that groundwater, and when I said before that everything we do is related to very slow laminar flow. So V is of the order of 1 meters per day. When you look in rivers, the velocity of rivers is measured in meters per second. When you're in aquifers, the velocity is measured in meters per day. So a meter per day is of the order of, 1 day has more or less 100,000 seconds, so it's 10 to the minus 5 meters per second, order of magnitude. So this term, V squared over 2G, would be 10 to the minus 5 squared, so it's 10 to the minus 10 square meters per second squared, velocity squared, times 2G is about 10 meters per second squared. So this V squared over 2G would be meters 10 to the 0.5, 10 to the minus 11 meters. 10 to the minus 11, what is 10 to the, so a meter, 10 to the minus 3 would be a millimeter, 10 to the minus 3 a micron, 10 to the minus 9 a nanometer. So I'm talking here, so 0.5, 10 to the minus 2 nanometers. You see, no, 0.05 angstroms. Is far smaller than a water molecule. So, I mean, adding a water molecule there, it doesn't make a difference in terms of, so I think we are justified. A true physicist would never accept that, but a geologist, for a geologist, it is sufficient. So we work, this is, in hydrogeology, in groundwater, this is what head is. And this concept, even this is too complex. So I'll tell you the real definition of head. So you have a well. You measure it with piezometers. Piezometers are holes that you open in the ground and you open at a given depth. And then, so water is flowing through here, whatever. And here you measure the pressure, and this point is at a given elevation C, with respect to, usually with respect to the mean sea level. And you measure the pressure as well. And presumably here you have a water level there. So you know that if you have a water level here, and the piezometer is open at the depth D, the pressure here will be D times the specific weight of water there, huh? Rho G. D times rho G. Therefore, head, which is P over rho G plus C, will be P over rho G is D plus C. So head is this elevation with respect to the mean sea level. This is head. So head is the elevation of water in wells. And this is the definition that geologists work with. Huh? Elevation of water in wells. And it is very handy. Still, you will find, and be prepared for this, you will find that people confuse, because this is not what we measure. What we measure, even if we have John to come up with fancy methods, what we measure is we measure the elevation of this sea top or sea, I don't know, sea top, let me call this sea top, and we measure this depth. So head, which is the elevation of water, is equal to the elevation of the top of the well minus the depth to water table. And it is very hard to convey that the depth to water table is not a state variable, doesn't tell you anything. So if I have a depth to water table, I don't know, 1 meter here, if I come up here, it will be 1.5, and the water has not changed. So depth doesn't mean anything. What counts is the absolute elevation of water. And you say, well, this is silly. Well, it is silly, but people get confused. 1, 2. Measuring this is extremely difficult. So be prepared to have big errors, not so much because of the measurement of the depth or whatever, but because of the measurement of the elevation of the point. And I have made some severe mistakes by believing that the, the surveying of the tops of the wells is correct. So much for head. Easy concept, elevation of water in wells. All the way down to energy per unit weight. So there is some fundamental concept there. So that's for the first thing. Yes, we have a potential as long as temperature or pressure, temperature or concentration are constant. Ooh. So second issue, what is it that opposes fluid flow? So now we have the potential, but our real issue is to know how much water is flowing and what is the resistance to fluid flow. Now, for that, to study that, I have to remind you the concept of viscosity. Viscosity as the resistance of things to slide. And I want you to think in terms of what is the resistance for something to move depending on whether it is lying on a fluid layer or if it is lying on a dry surface. And just intuitively, think of lubrication, things like that. If you are staying on a fluid layer, what the resistance to movement has to do with the velocity. At the beginning, because of inertia, it may take an effort to get things moving, but once it is moving, to keep it moving at constant velocity depends only on the velocity. While if you are on a dry surface, it depends somewhat on the weight, and it is not so much the weight when I pull. It is the resistance, which is the sliding coefficients times the weight. So these are two different things. So independently of the weight, if I pull at a constant velocity, the effort I have to make depends only on the velocity. While if it is dry, it depends on the weight. It depends on the shear stress, which is going to be proportional to the weight. So this is this is the fundamental issue here. And that is related to viscosity. And we could talk a lot about viscosity, which is, I guess, it would be the main topic of today's lecture. But I'm going to go quickly. All I want you to remember is Newton's law of friction. That basically tells me that this shear, the shear force I have to make, the shear force that the fluid exerts, a moving fluid exerts on a surface, and vice versa, that the surface exerts on the fluid, is proportional to this velocity gradient, to the derivative of velocity with respect to the normal to the surface. So if velocity is changing a lot, if there's a lot of shear in the velocity, I have a lot of shear stress. If it doesn't, then I have little shear stress and little resistance to movement. So this is the basic concept, viscosity. And the definition of viscosity is implicit from this law. So it's the ratio between the shear stress and the shear in the velocity, the gradient of the velocity or the derivative of velocity along the perpendicular to the surface. This is the concept of viscosity. And you can think, if I put here air, it will move very easily. So the shear stress that the air exerts on the air is very small. So this mu will be very small. Air has a very small viscosity. If I put here a very dense oil, yes, to move this, yeah, I would be basically dragging also the solid, so that this tau will be very big, even if the change in velocity is small. Therefore, the viscosity is very large. Air has very small viscosity. Heavy oil has a very high viscosity. This is the fundamental parameter. And it is good that it is only one parameter. And it has nice values, actually. So it's measured in poises. So yeah, it's 1 centipoise is the viscosity of water, or 10 to the minus 3 if you use international system units. So I will, yeah, it is also related to the origin of viscosity is also related to momentum conservation, but I will not get into that because the question is, how does this viscosity concept affect fluid flow? And here we have now a physician. He was interested, well, what is it opposing the blood flow in, or the flow of blood in the vessels? And this was Poiseuille, and he did experiments. He had to do it with them. He had to do them with water, because at the time, we are again at the beginning of the 19th century. There were no anticoagulants, so whenever he tried to do it with blood, the blood would coagulate, and he could not do his experiments. But anyhow, he did his experiments and found that the flow rate for a given pressure difference on the two edges of a capillary tube, the flow rate is proportional to the radius or the diameter of the tube to the fourth power, which is kind of weird. And then there was a German guy doing about the same time experiments, and from his experiments he found that it was to the power of 4.12. But he was an engineer. He was an engineer. He said, no, this number sounds too weird. It must be 4. He wrote it like that. I get 4.2, but I think it should be 4. I must say that this guy, Hagen, he was a very well-educated. So he worked with Bessel and with these fancy German mathematicians, and so he knew a lot of statistics. And in fact, he's the first guy who really formalized that why measurement errors should follow a Gaussian distribution, even though he was really a coastal engineering guy eventually. So, but anyhow, with all you have here, you could derive Hagen-Poiseuille law. You don't need any concept that I haven't taught. And the basic concept of this thing that the flow rate is proportional to the radius to the fourth power, and you can derive every coefficient, etc., is very easy. The whole concept, if you have a tube, or you can also do it for parallel flow, in which case it is proportional to the cubic power of the size. I mean, the basic thing is that if you have a slow laminar flow, you will have a parabolic velocity profile. So given the parabolic velocity profile and given the mean flow rate, it is very easy to compute this slope. And if you compute this slope, then you can compute the shear stress that is being exerted here as mu times derivative of velocity with respect to r in the case of a circular tube. And then you can say, okay, momentum conservation. Momentum conservation is that the forces that promote fluid flow, which I will have here a big P, P1, and here a smaller p, I am going to call it P2. So P2, or excuse me, P1 minus P2 times the cross-sectional area of this tube, times the cross-sectional area, which is pi r squared, should be balanced by the forces that oppose fluid flow. And the forces that oppose fluid flow would be this tau times the surface area of the cylinder, which is 2 pi r times distance. Let's call this L. And if you do that, but tau, I have to use this. Tau would be mu dvdr. Oh shit, dvdr. Well, I have to find this law of velocity. The velocity here will be some coefficient times let r goes from here to here, so it would be something like r squared minus r squared, something like this, so that the velocity is maximum for r equals 0, and it is 0 for radius equal to the radius of capital R, the radius of the tube. So all I want to point here is that this dvdr is going to be something times r, some coefficient times r. So, excuse me, capital R. So if I put it in here, this tau, and this will be proportional to the mean velocity. So mean velocity times r times some coefficient. This is the tau. So if I increase the velocity, the mean velocity, I am also going to increase this this gradient, and I am going to increase the shear stress times 2 pi r. So I am done almost. So what am I solving? Oh, yeah, mean B. So what I want is to solve for mean B. And mean B is pi r squared delta P divided by L, and then divided here. Shit, I am making some big mistake. This is not working. So pi I, sorry? I am making some big mistake because it should come, actually the velocity should be proportional to 1 over r squared.
So the derivative of the velocity?
The denominator has to be 4. Viscosity.
Yeah, viscosity should come here. So it comes here, sorry, viscosity comes here, the shear is proportional to viscosity.
Pressure acts over the whole surface, so pi r squared for the...
B over R.
What?
It's B over R. Yeah, that's B over R. So it's eta times B over R.
The denominator has to be r to the 4th.
Yes, yes. But it is not, it's r squared. I don't know where am I making a mistake. No, but someone said V over R there. Yes, I am making a mistake here. But no, I am not. This A,
Not capital R. It's more 2 times A. No, it is capital
easy. You see, you think the response to the question, if no one else asks it, what when things go wrong? And then people tend to be demoralized and say, oh shit, oh, my life is miserable. So this is to me is the main barrier to one's research. So here things are going wrong. What do I do? Oh shit. I start all over.
Look at what Filippo is saying. It's DVDR, but it's DV smaller, you know?
Yeah, no.
At the origin.
The capital R is a constant.
Yeah. So then you have to, but then you have to replace small r by r to
Yeah.
get something. So I think this is probably the source of the right?
You get all this noise from people telling you, oh, you should do this, you should do that. I don't understand anything you said. But the important thing, be constructive. If you solve the problem, say, Jesus, instead of doing this, do something else.
Shouldn't you just assume that dV over dr is scaling with the mean velocity over the radius?
Well, yes, clearly the mistake is here. But where was the mistake?
So it's A over r rather than...
So this is velocity that I'm using. So dV dr is equal to 2AR, okay? Now, I want to compute it at R equal R. So the value is 2A capital R. So I substitute it in Newton's law. I substitute it in Newton's law, and I get that tau is equal mu times dV dr for R equal capital R, which is mu times 2AR.
A scales with 1 over r squared, that's the trick.
What?
A scales with 1 over capital R squared.
Because you want to write velocities, like the average velocity.
Divided by capital R squared.
It has to be.
I believe it is 1/2. This is the equation. This is the question. Is the mean velocity, if you integrate a paraboloid on a circle, you should know it's 1/2 or 2/3.
Side and you have a discharge on the other side. That doesn't work.
Look at the
That's the
When we start bullshitting, you, Emmanuel, I am very disappointed at you. Well, mean velocity,
Don't you have the derivation of
I don't want it. I want to do it. This is the way it's done. Huh? Mean velocity is the integral of B of R times 2 pi R dr divided by the integral of 2 pi R dr. Well, this is clearly the area of the circle, which is pi R squared. And the integral of this, since B of R is that profile we had there, it was A R squared minus R squared. I think it was like that. And we agree on that. 2 pi R dr. The integral of this would be again A R squared. The integral of 2 pi R, this is pi R squared minus, and then the integral of this, which is a thirds, so it's 2/3, it's not 1/2, it's 2/3 of pi R fourth. So the integral of this is 2a pi, 1 minus 1/3 is 2/3 of a pi R squared. Fourth power. Yeah, we agree on that? What?
divided by pi r squared.
Yeah, divided by pi R squared, sorry.
So now you solve for
2/3. Let's do it slowly. Pi R squared R pi. Yeah. So this is the mean velocity. Why are we getting with it? Oh no, this is because you were giving me shit that the mean velocity was. So that's it. There you have the mean velocity.
now you solve for a, and a goes like 1 over r squared, see?
Yes.
And then you substitute and you have your r squared that solves the problem. See? So you solve that thing for a, and you plug it in the law for v, and then it works. A is 3/2 of V bar over R squared. And then you plug that into the law for the velocity that you postulate. And then it's proportional to V bar over R squared.
You understand? So basically, this is what he has been telling me all along, that A should be proportional to 1 over R squared, and actually it's a factor of 3. Just to make it things short, then tau is inversely proportional to R, which makes sense. Which makes sense. If you have a big tube, for a given velocity, you will have a small resistance. If you have a small tube, you will have a much larger resistance. And then, so this tau is proportional to over R, and then when I make this equilibrium, basically, remember, we are doing, the whole point was to do this equilibrium of forces. The forces I apply, the pressures, are equal to the resistance to the fluid flow, and so I solve for the mean velocity, and the mean velocity, this is the tau I put here, so this is what I have to plug in this equation, and then I can solve for the mean velocity, and I get that the mean velocity would be R cubed. So this is the mean velocity, the flow rate, which is pi R squared times mean velocity, proportional to R. No, I didn't want to write it, but I got covered. And it is also the basics of Darcy's law. This is the way of, so what I want to say is that essentially Darcy's law, like Hagen was saying, comes from the equilibrium of forces. So if you do an equilibrium of forces across the porous medium, and you realize that the shear stress that the solid is exerting on the fluid is proportional to the velocity gradient, but the velocity gradient, and this was really the important thing here, is proportional to the mean velocity. If you multiply the flow rate by 2, you will also be multiplying this shear stress by 2. So in the end, Darcy's law, really what Darcy's law expresses is an equilibrium of forces thing. We call it momentum conservation, but really expresses equilibrium of forces. Forces that the water, the pressure, facilitates fluid flow is compensated by this shear. So effectively, when you do hydromechanical, this will be important, I guess, is next week when you will do hydromechanical. Darcy's law is mechanical equilibrium forces. It's a force that the water is, or the fluid is exerting on the solid, and vice versa, that the solid exerts on the fluid. Just one comment, and then I will finish. An additional comment. What if density depends on temperature and concentration? The point I wanted to make is that then you have not a single potential, and this will be relevant for seawater intrusion and these kind of things. In that case, we do let us look at the equilibrium of forces along the vertical. When you do the equilibrium of forces along the vertical, basically the forces in place are the same as we had before. Some pressures acting, viscous forces opposing fluid flow, but you also have the weight of water there. And the weight of water, which is this additional term, if density depends on variables other than pressure, it will depend on variables other than pressure. And I cannot write then everything as a function of head gradient. So effectively, the right form of Darcy's law with that is when you apply this equilibrium of forces here, again, equilibrium of forces, is that you have put here a density. And what is really puzzling, what no one really understands, not even people who write density-dependent flow codes, is that this density here is not the density at the point.
It's not what?
The density at the point. It is the density, the mean density along the vertical. And the fact that it is along the vertical is frustrating. It is frustrating because if I have 2 points, the average density I will see along the vertical will be different depending on the path I take. And this thing that the potential difference depends on the path kills us, because we are trained to think in terms of we have a single potential. forget it. When you have density-dependent flow, you do not have a single potential, and you have to look at the density in every point and integrate along the vertical and realize that whether water comes from here to here, from the upper point to the lower point, or vice versa, depends on the path. We will have a rotational flow, and when we deal with density-dependent flows, we do have rotation even in homogeneous media. And this will be it for it. So temperature will affect this density and will affect viscosity very much. In fact, it is a dramatic effect on viscosity. For oil, you can all think, if you like to cook, the oil when it is cold, it moves slowly, but when it is hot, it moves very easily. This means that the viscosity drops significantly. And for water, oh, sorry, I'm going the other way. For water, I think I have here, yeah, it's my rule of thumb is that every 20 degrees, it's a factor of almost 2 for cold temperatures. The slope actually goes down. So simply by heating water from 10 to 30 degrees, you increase the hydraulic conductivity, you increase the viscosity, you decrease the viscosity by a factor of 2. When you heat, viscosity goes down. So,
what's the impact on density at the same time?
Say again?
For the 30 degrees rule that you said, what would be the impact on the density?
It's the temperature doesn't affect. It affects a little bit. It's I don't remember. I guess it's 10 to the minus 5. No, the expansion coefficient. So it would be 3 10 to the minus, about 10 to the minus 3.
Much less. It will be much less.
Well, it is different because viscosity. Yeah, viscosity affects the resistance to flow. So viscosity is here. So by decreasing viscosity, the fluid moves more easily. By changing the density, you are changing the forces involved in the. So it's. The whole thing with density, the density variations, all these things don't need your brains too much. It is only relevant when you have a vertical dimension which affects whatever. So it's and it can be relevant in some cases. For most cases, it is not a very critical issue.
A bit about non-Newtonian flow.
Today, if here, you will be talking a lot about non-Newtonian flow, I hope. Or Michel, will you? You will be talking about non-Newtonian flow. So, yes. So, basically, Newtonian is when Newton's law is valid. But sometimes this viscosity or this coefficient will depend on the velocity itself, will depend on the gradient of the velocity, will depend on other things, and then this law is not valid. For all fluids, for most fluids of practical interest, water, beer, wine, Newton's law is valid. But, oil people, they work with muds, they work with, physicians work with blood, and then in those cases it's not.
Say non-Newtonian fluid, or because you're talking about fluids now, and non-Newtonian, you say non-Newtonian flow or non-Newtonian fluid?
No. Whether Newtonian or non-Newtonian, this is a property of the fluid. So some fluids obey this law, some fluids do not. And then you call them Newtonian fluids or non-Newtonian fluids.
Just a quick follow-up on the.
Do you get the R4 law anyway? If you are in an ideal capillary and you put blood through it, since blood is not.
No, for blood it doesn't work. Blood is frustrating. Sometimes you see a red cell like this, and you see a capillary tube like this. There is no way. And it shrinks, it deforms, it gets there. But then the point is that this whole thing with the parabolic velocity profile is not true. Because red cells alienate to move, and so it's No, blood definitely is not Newtonian fluid, and in fact, there are people who use the non-Newtonianity, whatever, as a clinical tool. You look at the physical properties of blood to tell whether you are sick or not, and there are some sicknesses that are best diagnosed by looking at the rheological. Rheological properties means how does this mu depend on the velocity and the velocity gradient. About these physical properties of blood can be used to diagnose whether you are. I don't know. I'm not expert in this.
So just to be clear, Jesus, normally we define a datum, and then we would define the potential energy by the local density times the distance from the datum. And then we would define the pressure potential by force per unit area. Are you saying then, just so the students are clear, that if you define everything from a datum, you'll get the wrong answer? I think that.
Well, you get a number which is useless. Yes, and no, but the question is very good because this is a source of big mistakes. So we go back to our piezometer, and I have a datum. Usually it's mean sea level, whatever. And I measure here the pressure, and I measure here the density. And then one would say, okay, head is equal to C plus this P divided by rho G. You got a number, which is very useful if density is not changing because of temperature or concentration. If it does, you're in deep shit. First of all, what we usually measure is not, you don't put a pressure sensor here. What you usually measure is this depth. And the pressure here will depend on the density here. So effectively, I said before, well, the pressure will be equal rho G times depth. I said being depth this. In reality, the pressure is the integral of rho of C times G times dc. Let me call it with another name, zeta, where zeta varies from the C of the piezometer to whatever this is upper limit is, to h. So the point is that when you measure the elevation here, just to know the pressure, you have to know this. And then basically this is not too bad. You do you can do it with a diver, with a sensor that measures pressure and salinity, temperature and salinity. You can get it. In fact, they are called CTD. CTD is the name of this sensor. This is a sensor that oceanographers use, and they are conductivity, temperature, depth. That's what CTD stands for. So you use CTDs to obtain basically the conductivity and the temperature versus depth, and that allows you to compute the pressure. Yet, and then say, but I also measure the conductivity here, so I know the conductivity, the density at this point. If you apply this number, H equal C plus P over rho G, at this point, you get a number. This will not tell you whether water is, and you do it in another point, it's not going to tell you whether the water is going to move this way or that way. And think that we have the C here, and we have let me put the C on this side. So we have an interface like this. So we have our piezometer in the seawater zone, and you have the other piezometer here where you also measure pressure and temperature on the freshwater zone. If you do the comparison between the pressures this way, you say, oh, if I come this way, I would need colors now, because this is getting to no color. Oh, good, we have colors. Thank you. If you do the comparison this way, you will say, oh, I have heavy water, heavy saline water coming. So you would tend to think that water moves this way. If you do it like this is very light, so water would move like this. So where is water going between A and B? Is it going from A to B or from B to A? And it can go both ways. So you can have these convection type cells. And we do have these convection type cells that you can go both ways. And it is in heat transport, they are well known now. So it's, but also for seawater intrusion, you have these convection cells. The essential point is that once rho depends on temperature or depends on concentration, you do not have a single potential. You have to think that you need both pressure and the distribution of densities to know which way water is going to flow. And this is the right way to write. Of course, if rho is constant, you can bring it inside the gradient and put here, well, this is the vertical component, so you can put here P plus rho Z, which is basically head multiplied by rho G. Yeah? So when density depends only on pressure, yes, you can go back to the traditional form of Darcy's law. But when density depends from some other variable, no, these two terms, you cannot mix them together.
But let's keep the fun. Let's keep the fun.
That is a lot of fun because it gives rise to many things which are, well, I don't know you guys, but I am not used to think in terms of two potentials. So, so it gives things to some counterintuitive things like this convection cells. But people who are trained in thinking this way, they find it natural.